Hello and welcome. My name is Matthew Hershey, and you are watching another installation of our virtual meetup series. Today, I'm quite excited. We have Professor Klaus Wilke from UT Austin, who will be joining us today to tell us a little bit about data visualization. Before I bring Klaus on, I want to remind you of a couple of things. First is we are now live streaming these to YouTube directly rather than using another platform and uploading them later. Hopefully this allows more people to access this information, find it easier, and learn from us as we go along this journey together. The second thing is we are starting a new community, a new website, where we're bringing together people who are interested in finding complex, taking complex data and finding signals in those data and bringing them all the way through this process to data visualization. This website is called Eureka Labs. That's Heureka Labs. I'll be sharing more about this in the description below and providing some links. But I want to share with you first because we're quite excited about bringing people together. And this will be discussing ideas related to thinking and creativity and patterns and all things related to the data science, data exploration, and data visualization processes. So look for some more notes about that coming soon. Without any further ado, I'd like to welcome our guest today, Klaus Wilke. So Klaus, welcome.
Yeah, hello. Thanks a lot for bringing me on.
Absolutely. Before we get going into your presentation and discussion of some principles of data visualization, especially using color for data visualization, I thought I'd first let the audience get to know you a little bit. So why don't you first just give us a very brief background?
Okay, yeah. So I am originally a physicist. Both my undergrad and my PhD were in theoretical physics. Doing my PhD, I sort of started drifting into biology, and then my postdoc was biological. And now, since 2005, I have been a professor of integrative biology at UT Austin. Most of my research is broadly computational biology, molecular evolution, not really tied to any particular model system. It's just a lot of theory, computation, just being a physicist trying to pretend to be a biologist mostly, I guess. And the data visualization has always been sort of a hobby. Lately, maybe it's a bit more of a serious hobby. When you're really serious about a hobby, sometimes it becomes unclear where the hobby ends and the profession starts. But I still see it mostly as a hobby, something that I enjoy and spend some time. And it also gives me the opportunity to think about something else than, say, the biology that I mostly think about day to day.
What are some of the scientific questions that you and your lab are interested in?
So the broad question, there's a couple of secret projects that I can't tell you about yet, but I guess the things that I can tell you about, one is trying to link protein biochemistry and molecular evolution. So in the molecular evolution field, there's a long history of treating biological sequences just as strings of letters. It's basically computer science. If you read, say, what phylogenetic tree reconstruction literature, what they do, it's basically completely devoid of any biophysics, any biochemistry. And so what I'm not working on phylogenetic tree reconstruction, but I'm working on trying to bring some biochemistry and some physical objectness. A protein is an object in 3D space that interacts with other objects. And so how does that shape the evolution that you see at the sequence level? That's one thing. And the other thing is we're trying to simulate cellular processes and cells. Mostly currently we're simulating bacteriophages, so viruses that infect bacteria as they infect bacteria. And it's a nice model system because they're sufficiently simple and small that you can actually pretty much simulate the whole thing. So that's another sort of major direction in the lab.
So it's obvious to me that there's some direct parallels between some of the challenges you have in your own scientific work and challenges with data visualization. In order to, the whole data visualization field essentially sprung from this challenge of visualizing really complex things. And what I can glean from what you're able to tell us is these are complex projects. You've got a lot of different types of data, whether strings of letters, and then trying to think about them in 3D space. You need to then think about how to construct and how to interrogate some of these complex data challenges, it seems.
Yeah, I'm not sure that they're any more or less complex than what you would find anywhere in biology. I think biology over the last 15, 20 years has just, in general, gone into this direction where data sets are massive, high dimensional. So you basically, everybody has that challenge, I think, of trying to visualize these massive data sets. I'm a bit, what's the right word? So there's this tendency that I see in particular in, say, high profile publications in Nature or Science or so, that the experimental setup is one that creates massive amounts of data, and then you have these high dimensional data sets and you visualize them and you get these beautiful, colorful images that nobody can understand. And that, I think, is actually a bit of a problem for the field. And so I'm actually very much in favor of very simple visualizations. I think if a visualization looks great, but it takes you a day to figure out what it actually means, then there's a problem. One that we run into in our group meetings all the time, like we have every week, we present a paper, and just so often that somebody has this very confusing visualization where we all sit there and we say, we have no idea what's going on. So that's something that, I mean, that we're not really going to talk about that today here, but it's something that we all need to keep in mind, that oftentimes simple is better.
So I think you're referring to like a temporal t-SNE plot or something like this.
Yeah. For example, right? What does that mean? Nobody knows.
Right. Anyhow, so you started this as a hobby. This data visualization work is a hobby, but you've gone quite deep into this hobby, writing books and having an active blog and sharing information on Twitter and all of these things. So when did that transition happen? How did that occur?
I think that it was sort of a long, drawn out process that. So I had to do a lot of visualizations all my career, obviously, and then I would work a lot with students to make visualizations, and so I would find myself saying the same things over and over, like things that I had to criticize in their visualizations. And so at some point I said, well, maybe I can help them if I write an R package that sort of automates certain things. And so that got me into this whole business of writing R packages. So the cowplot package that some people use, by the way, that's just my initial, COW,
yeah,
cow. That was, I think, actually my first R package that I ever wrote. Like, don't look at the source code. It's pretty scary in places. But basically, we're using ggplot at the time, and there were things that I wanted to do with ggplot that I couldn't do. And so I wrote my package that fixed some of those things, and then also set up a theme that I liked and so on. So basically, the initial philosophy of cowplot was like, you're allowed to break any rule of good practices of programming if the outcome is what you want. So that's sort of the design of cowplot. And that grew. And then over time, I actually realized that if I make changes directly to ggplot, that's often the better approach. And so in my mind, there's now a very clear distinction. Like, if I do something that is like well thought out and properly implemented and clean and fits into the ggplot code base, then that's where it goes. And if it's just like another weird hack to allow you to do something that otherwise you couldn't do, then it goes into cowplot. Right. And then I wrote the ggridges package, and that was actually, so at some point I decided to write this book on data visualization. That's actually something that I've wanted to do for a really long time, probably like honestly 15 years or so. And I never really had the technology that would have made it sufficiently easy that I was really willing to do it. And if I had done it in 2005, I would have written it in LaTeX. I would have had to draw a lot of figures by hand. It would have been extremely laborious, and I just didn't want to do that. But then when I started writing this book, that was maybe 2017 or so, I felt that with R Markdown and ggplot with a very healthy ecosystem, that's the word, ecosystem of extension packages and so on, I could basically write the book all in R Markdown. I didn't really have to post-process figures. They would just come out the way I wanted. And so there for a while, like, I was in stealth mode, as you would say, where like I was working on the book but not telling anybody. And during that time, actually, I was doing a lot of stuff on Stack Overflow, for example, answering questions, because that was actually me training myself, trying to figure out, like, if somebody posted a question, I was like, I might want to have something like that in my book. I would like figure out if I could do that. And so then I wrote ggridges, because I knew that I wanted these kinds of plots in my book. And so there was no obvious package that could do that. So I wrote that, and that's how it developed. And so really, like, my involvement with ggplot happened during the time of writing the book, because I would encounter these things where I was, oh, it would be really good if I could do this. And I made a pull request to ggplot. And so that's how, like, I got sucked into that, I guess. Yeah.
So today you're going to tell us a little bit about data visualization, and particularly color.
Yeah.
So I want to mention, before we turn it over to you, I just want to mention to the viewers that I'll be manning the chat board. And so if you have comments or questions, go ahead and ask them in the middle, and we can interject and have Claus provide more detail if things aren't clear. So with that, Claus, I'll turn it over to you, and go ahead and tell us a little bit about color.
Yeah, so I simply just called this colors today because I think that's all we're going to get to today. So this is actually a section out of a longer talk that I often give. Actually, not, I shouldn't say longer. So normally it's about an hour-long talk that has a little section on color. And every time I give that talk, I have to rush through colors. And it's such a complex and interesting topic. And so I thought today, let's just spend a whole hour or however long this is going to be on colors, so we can really dive a little deeper. So let me start with just the basics. And so there's one important basic concept that comes before anything else, which is using colors for data visualization is different from using colors for, say, painting or interior design or setting up a movie scene, in the sense that in the context of data visualization, typically we actually have data values that we want to represent with colors. And that's very different from we're just using colors to create an atmosphere or a particular visual composition or so. Now, when we make data visualizations, we also want to do the design aspect. I mean, we typically want to use color to convey data and create something that looks good, but it's sort of a secondary point. It's not the primary point. And so it's really important to distinguish that. And so with that, we need to, let me see if this advances. Yes. We need to think about what are the main uses of color in the context of a data visualization. So again, like, there's a use of color of I want to paint my bedroom, but that's a different, that's not today's topic. Though possibly you may learn something about colors that you can apply to that. We'll see. So in the context of data visualization, the first one is you may want to distinguish categories. So you have different things, say, different sports, cycling and running and weightlifting. And so you represent each with a color. These are distinct categories. And so I'm showing you here on the right a little color scale as an example, and I'll go into more detail in a second. So the next one is we may want to represent data values. And it says in parentheses sequential because there's really two different ways that we can do this. So that might be something like I want to encode, say, the number of people that live in an area by the color that I shade that area with, right? And so then maybe dark means a small number of people and light means a large number of people or something like that. So now each color is actually a numeric value. Here in the categories, each color is a categorical value, right? Like a level in a factor. So as I said, weightlifting, running, cycling, and here now it's a number, 5, 7, 200, whatever it may be. Now, closely related is we may have a diverging scale. Actually, and there's one that I don't go into. You can also encode 3 dimensions in color, but I'm not getting into that today. So diverging is essentially actually still 1 dimension, but you specifically highlight that you're going in 2 directions, right? So for example, if you have a correlation coefficient, you may want to clearly distinguish positive from negative correlations. Or in the context of biology, gene expression levels, they can go up or they can go down, and you may want to encode both the value by which it goes up or down, but also separately the direction, up or down. And so that's a diverging color scale. And then the last one is you may want to highlight. So that's a special form of categorical scale. The difference is that in a normal categorical scale, you're actually explicitly not highlighting. So point number 1, distinguish categories, I just want to distinguish without highlighting any particular one. Highlight means I do also have categories, but some categories in some form stand out from others. So with that, let's just go through those in a little more detail. And basically the main point is, if you're using color in a visualization, the first thing you should ask yourself is, which of those 4 uses am I using? And if you cannot point out that you're doing one of those 4, then first of all, maybe you shouldn't use color in this particular context, or you should think more clearly about what it is that you're doing. Maybe you're doing one of those 4 and you haven't figured it out yet. So now let's assume you know what you're doing. So for example, you want to distinguish categories. Then you need a color scale that can do that. And what I'm showing you here is 3 different color scales. First one is the Okabe-Ito color scale. That's a color scale that I really like, that I'm using in my book throughout. It's relatively easy. The colors are relatively easy to distinguish for people with color vision deficiency, color blindness. So that's why I like to use that. Then there is another color scale that is very popular. It's from the Color Brewer system. So Cynthia Brewer, that's, if you don't know why it's Color Brewer, it has nothing to do with brewing colors. It's Cynthia Brewer is her name, and she made these color scales that were specifically for maps. In the context of maps, if you highlight, if you show countries in different colors, that's a categorical problem, right? And so she developed various scales. This is one of them. And then here's the ggplot hue scale. That's actually the default scale in ggplot. If you need a categorical scale and you don't tell ggplot anything in particular, it will generate the scale, which, by the way, does not work that great for people with color vision deficiency. The main point of the hue scale is that it has certain mathematical properties that make it a nice default scale, which you almost always want to switch out then in practice. So the first lesson that I would say I have for color use in general is, once you know what your use case is, for example, distinguish categories, it's a really good idea, honestly, to use a professionally designed scale. Like, go through, say, maybe use the Okabe-Ito if you like it, or go through the Color Brewer's palettes and pick one that you like. It's actually quite difficult to design a color scale well. And I'm not saying you shouldn't. If you want to go through the effort, and I'll talk a little bit later about how you might want to do that, that's all fine and good. But if you haven't studied colors that carefully, you're better off using an off-the-shelf scale that is good than using a scale that is not good. So it's a good default position to use an existing scale that is good. And these 3, they're reasonable. Okay, so here's an example. This is from the longer talk. By now you would have seen this plot and I would have discussed it, but we don't really have to. The main point is there's two different lines and they're two different, it's preprints and different preprint servers. And I'm using color to distinguish the two lines without highlighting one particular one. They're standing side by side and color helps us distinguish them. By the way, in the way this figure is drawn, we don't need color to distinguish them because the lines are labeled. If I printed this out in black and white, you would still be able to see this is the one that corresponds to bioRxiv, this is the one that corresponds to arXivQBio, but the color helps you visually to make this distinction. And so it's a good use of color in this case. The other one, this is a figure that in the other talk, I spent a long time explaining why this is maybe a dubious figure. I'm not going to do that here now. So this is not necessarily a good figure. It's a highly confusing figure, but it uses discrete colors here. We have airlines, American, Delta, and other. And these three airline groups, this is all others. Again, we're not highlighting any particular one. We're just showing them side by side. And so we're using three different colors. And these are three colors from the Okabe-Ito scale, by the way. The same was with the previous figure, three colors from the Okabe-Ito scale. Okay, now one important thing is you can only distinguish up to about 7 categories with colors. So whenever my default answer when people ask for categorical scale is always use the Okabe-Ito scale. And then they say, oh, but I have 52 different things I need to distinguish. And Okabe-Ito has only, I think it has 8 colors, 8 or 9. Definitely does not have 10. And my answer then is don't do it. So, but here's an example of how you could do it if you wanted to and why it's silly. So I'm showing you every state in the US. And I'm showing you along the x-axis the population size in 2000 and along the y-axis the population growth from 2000 to 2010. So each dot is a different state. They all have a distinct color, but it gets quite tricky to read, right? So, okay, which is this state here? Well, it's sort of a pink. I don't know, maybe it's Ohio, maybe it's Utah, maybe it's Montana. I have a really, really good screen here that has really good color resolution, and I can sort of see that probably this is Ohio. It sort of looks the same, and then, but this one over here, maybe it's Delaware, maybe it's Iowa, maybe it's Alabama. I'm not quite sure. It gets really complicated, right? It's not really easy to read. And now if we wanted to, we could probably turn this into a puzzle game and wait long enough. And this over here, what is this? Is this North Dakota? Well, it's one of the most populous states and has grown a lot. It's probably not North Dakota. Maybe it's Texas, right? But now we're actually using auxiliary information. Like the color really doesn't help us distinguish these categories. So I would argue that you should not do that, right? You should rethink your visualization. For example, I could use 4 different colors to highlight different regions, and then I could do some direct labeling to label some of the states, right? And so this is Texas here, as I predicted. This is California. But this is actually now a more useful visualization. For one, because even though I'm not calling out every state, I'm calling out enough states that you can actually, there's a good chance that, one of the states I'm calling out is a state that you live in or have lived in or have a relative in or so, and so you can connect to that. And also because I'm highlighting the regions, you can actually see patterns. Like the West over here has systematically experienced the highest growth, and then the South has also experienced a lot of growth, versus the Northeast has not experienced a lot of growth. But in terms of population size in 2000, all 4 regions are mostly represented along the entire spectrum from quite small to quite large, maybe with the exception of the Midwest. There isn't a really, really large state in the Midwest. Well, I guess Pennsylvania in 2000 was the 5th most populous state in the US. So there's a lot of patterns that I see right away if I use 4 colors, but if I go back, if I use 50 colors, you would spend a day trying to figure out these patterns, right? So don't do that. Use colors to highlight small numbers of categories. 7 is already a stretch, honestly, in my opinion. Okay, now color to represent data values, sequential. I'm again showing you a couple of existing scales. So this is another color scale from the Color Brewer project. So this is now a sequential scale. It's called blues because it's blue, right? It goes from dark blue to light blue. There's a different color scale, heat. It looks kind of like cold and hot. And then the Viridis color scale, which has been very popular recently, which goes from sort of a dark purple to a very light yellow. If you have a sequential scale, the important thing is that like here I'm showing you 7 points along the scale, right? And if I take one step, like from here to here or from here to here, I want the change in color to be approximately the same. So this is called a perceptually uniform color scale. So like let's say if this is units, if this is say units of 10, so I have 10, 20, 30, 40, 50, the jump from 40 to 50 is the same as the jump from 10 to 20, right? So in the color, it should look the same, perceptually uniform. And again, there's many color scales. Some people argue that Viridis is the perfect scale. We can debate that. The truth is every color scale, that even well-designed color scale has strengths and weaknesses. There's things that I don't necessarily like too much about the Viridis scale, but it's a perfectly reasonable choice. If you don't know what to use, better to use Viridis, or there's like various options from the Viridis family. There's one that is more like a heat version with the purple to red and yellow. Those are all good scales. And so I'm showing you here. So one thing that I noticed when I was working on my book, I would like make a figure like this. For example, this is the annual median income in the various counties of Texas in US dollars. And I would try 50 different color scales on this image to see how they look. And what you notice is, so this is a perfectly reasonable visualization, right? There's a pretty uniform color scale. We clearly see here, this is the Houston area. This is just northeast of Dallas. It's basically the Dallas area, the Austin area. Those are the richest areas in Texas. And we can see that very clearly in this color scale. This is a reasonable choice. But if you flip through different scales, you see that they all give their own character. So for example, here, this is very calm, a very like calm and pleasant visualization versus this is sort of more aggressive, more in your eyes. The pattern that you see is roughly the same, right? But here the rich areas light up versus here the rich areas are the darkest. And then this is the Viridis. The Viridis does, in my opinion, bring out the gradient from richest to poorest a little better than, say, this one. It doesn't really show the gradient so well. It highlights the richest areas a little more and then shows the rest more uniformly poor. That's how I perceive it.
Claus.
Yeah.
We have a question from the audience asking,
okay.
Do you think that there's a common rule that says dark equals high values, light equals low values? Do you think that there's something consistent about that?
So that's something that I actually pondered a lot. Some people will say it depends on the background. Like if you have a white background, then light is a low value and dark is a high value. And if you have a dark background, then it's the other way around. I'm not entirely sure because by that rule, this figure here would not work, right? By that rule, this figure is exactly the wrong way around, but I actually think it works. And I think the reason that it works is that I've colored such a large area. that the background is essentially irrelevant in this case. The background essentially is dark in this figure because the majority of the counties in Texas, first of all, it takes up a fairly large area on the screen, and the majority is dark, and so the light areas, the high value areas, stand out.
So the challenge now, of course, is that several of our computers are now switching from daytime mode to nighttime mode, switching the colors. So depending on if you view the image in the morning time or in the evening, it will depend on the interpretation, perhaps.
Yeah, I mean, honestly, I thought about this a lot and I played around it a lot. And in my book somewhere, I make a comment to that effect. I think there's a tendency towards like dark works as high value on a light background and light works as high value on a dark background. But I would say just like look at the figure, see how you perceive it, see how some colleagues perceive it. And like if they all perceive it the other way around, then maybe there's a problem. I could also see that, I presume most of us know this dancer optical illusion where you don't know whether it turns one way or the other. I could see with this kind of situation that you get the same thing, that it could flip depending on how long you look at it or what kind of is going on in your mind as you look at it. You might perceive the light colors as high value or as low values.
Well, we just had Cedric Scher chime in, who's joining us in the chat.
Okay,
and
very
he agrees
good
with you in that half of the time people think one thing, and half of the time people think the other thing. So it turns out that it's consistently inconsistent.
Yeah, and so I mean, you know, there is, in the end, there is an element of design and of choice. Like I know Cedric likes sort of dark backgrounds. His figures oftentimes have dark backgrounds. I'm not at all a dark background person. It's just, I don't know, like it's not me, but that's okay, right? They can be all totally valid visualizations. And at the end, we can make a design choice, and that gives it our own personal flair or our own personal identity on top of the valid visualization of the data. So now let's go.
For clarifying.
Let's go to invalid, right? The rainbow. In my book, I label bad like any figures that have some questionable aspect to them that might lead you to misinterpret what they show. So this is a traditional rainbow color scale. And the first thing that you may notice when you look at it is it actually is essentially circular. You start with red and you end with red. So the data values at the two most extremes have the same color. So that obviously is a problem because the richest county and the poorest county have almost the same color, while intermediate counties have intermediate colors. And then this scale is very much not perceptually uniform. So you see how you go, like there's a lot of green here, and then very quickly it transitions to blue, but the blue is quite narrow. It's a very, very narrow range of values, and then you go back to red. And so what that does is the counties that happen to be just in the range that is blue really stand out from this large green background. And so this strong gradient that we had with the Viridis scale really totally goes away with the rainbow scale, right? And also the Viridis scale was very clearly highlighting the richest counties. And then it's also nicely showing this area over here. So this is Midland, Texas oil area. It's not the richest area in Texas, but there's a lot of wealth. And so you see a nice accumulation here of slightly more intense colors. And I guess what the rainbow scale does is it makes this area look just as rich as this, if not, sorry, got confused with my pointer here. This area looks just as rich, if not richer, as this one or this one, when actually these are the richest areas. So it's highly misleading. Don't use the rainbow scale. Okay, so the next one, color to represent diverging data values. That's essentially you're stitching two diverging scales together in the middle. So here I have like a light gray in the middle, and then it goes towards a green to the right and towards a purple on the left. Or here, this one goes to some sort of blue on the right and a brown on the left, right? Two sequential scales stitched together in the middle. And those are good if you have something that has a natural midpoint. So here I'm showing the percent identifying as white in Texas. And so that has a natural midpoint in the sense that if 50% identify as white, then the other 50 identify as not white. And so you have basically even numbers here. And so then you see along the Mexico border, the majority does not identify as white. And then towards the northeast, Dallas and so on, and then towards the east, that's where you have a majority white. Different color scales showing the same thing. I find this a little unpleasant, but it actually it looks better on my laptop screen than on my separate monitor. So that's a weird thing with colors. You can never really be certain that they look the way that you think they look. If I look here, this is just too bright and too kitschy. I would never want to see this figure realistically anywhere. Whereas over here on my laptop, it actually looks perfectly reasonable. So yeah, you can never be certain with colors. And then a blue-red, that also looks fine. Now, interestingly, with diverging scales, often rainbow is bad. Again, it doesn't make sense. Diverging scales, you can sometimes get away with using a sequential scale, and it may work. So, for example, this now does not look at it as a diverging situation. It just looks at it like a linear situation from 0 to 100, and that sort of conveys the same message as this one, right? If we sort of go back and forth, it's not that different. But the diverging scale, the advantage of the diverging scale is to really highlight the extremes here and take away the midpoint, versus the perceptually uniform scale doesn't really highlight any particular area. It just shows everything sort of at the same intensity. Okay, last one, color as a tool to highlight. So there, what you want to do is you want to have a set of colors that are extremely, extremely subdued, and then another set of colors that are very strong, very bold. So we have Okabe Ito accent. So what that is color scale that I invented. I just took the Okabe Ito scale and set of colors, I really desaturate them, made them very light, and then another set of colors that are made stronger. And so now I have two sets of colors that actually go together, but they can be used as accent colors and background colors. Or another thing you can always do is you can just use grayscale and then add in some very strong colors. Now there's the color brewer accent scale, which where the first 4 colors here are the low intensity colors, and then the last 3 are the high intensity colors. This color scale looks reasonable in a color palette, but I actually think it doesn't work very well, because actually these colors here are not sufficiently subdued. Like if you compare these to these, right, these are much more subdued than these. And you may think that, well, these are so drab, like why even bother giving them a slightly different tint? But if you use them in a visualization, so there's sort of a pet peeve of mine. When we color large areas, most of the time, unless we've really thought about it very carefully, we tend to color it too much, provide too much color. And so that's what the color brewer accent scale does here. Actually, I don't now have an example of this. It's in my book. I can probably pull it up in a second. But this is just a very simple example. So this is back to the airline example. This figure just shows that in this particular data set, American and Delta have the shortest delays. So this is the mean arrival delay in minutes, and they have the shortest delays. And I drew them in red to highlight them, and then I drew everything in gray. there's really no good reason to use different colors here, because this whole group, I don't really want to distinguish between them. So this is a scenario where I really only need two colors. The two that I want to highlight, I could have given them different colors if I wanted to, and then the rest that I don't want to highlight. Okay. Now, in general, so that was the 4 different color scales. In general, you want to be very careful with red-green contrast. And so that problem arises primarily in diverging scales and when you want to have different categories, right? If you stop somebody on the street and you say, tell me 4 colors, almost certainly 2 of the 4 colors will be red and green, right? They maybe they will say red, green, blue, yellow. Okay, there you have red and green, which is a red-green contrast. Or when people want to do diverging scales, almost everybody instinctively picks red and green. So that's for years been the standard in biology with gene expression levels. Green is up, red is down, or like green is good, red is bad, right? Traffic light, green is go, red means stop. It's just red-green contrast is so ingrained in us. And part of the reason, I think, is that everybody with perfect, let's not say perfect, everybody with regular color vision perceives the red-green contrast as extremely strong, right? If I take a red ball and throw it into a green lawn, somebody who can see the difference between red and green will pick out the red ball immediately. It stands out like a sore thumb. But if you have red-green color vision deficiency, you don't see the red ball at all in the green lawn. And so that's a problem. When we design color scales, we need to think of the people that maybe cannot distinguish red-green gradients. So here is a simulation of the color scale on the left for somebody that has difficulty seeing red-green color contrast. So let me pull up, there's actually 2 different ways in which you can be. So we ordinarily see red-green colorblind. So you can either have a deficiency in seeing red colors or you have a deficiency in seeing green colors. And both lead to the same outcome, which means you cannot distinguish red and green. So if you're in either of those categories, this gradient here will actually look like this or like this. The contrary is, if for you this looks like this or this looks like this, you are probably colorblind. Like there may be somebody on this call who didn't know, but is now saying, well, I don't understand anything. All these things look the same to me. If they all look the same to you, then you have difficulty seeing both red and green colors. Now, there's a third way of having difficulty seeing colors, which is not being able to perceive blue colors. And if that's your problem, then actually this particular gradient works. So it doesn't quite look the same. The red actually looks the same and the green starts to look a little different, but you can see the difference because the difference is between red and green, and you can see red and green, you just can't see blue. Now, there's ways around this, and the ways around this is, so color blindness is a bit of a misnomer because people are not blind to all colors. People just have diminished capacity to distinguish colors, and in particular, certain colors. So you can actually, let me step back. Oftentimes, the quick response is, oh, don't use red-green contrast because they don't work. That's a very, very simplistic answer. You can use something that looks like a red-green, oh, sorry, this is one comment. 5 to 8% of men are colorblind. So if I'm talking to a group of, say, 100 people, there's probably 5 to 8 people in the group. Now I assume it's 100 men. So let's say it's 50 men and 50 women. So maybe there's 3 to 4 men that are colorblind, and women are more rarely colorblind, but maybe there's also 1 woman who's colorblind in my audience. So you can construct red-green gradients that aren't pure red and green. So for example, this one here, this is actually purple, and this is a green with a yellow component. So purple is a mix of red and blue, and this here is a green that has some yellow mixed into it. In this context, it's actually both red and blue together make yellow. And so, did I say this right? I may be confused. So ignore what I just said. In any case, this is a green with a yellow component. And so for people that cannot distinguish red and green, they can totally distinguish that as a blue over here and a yellow over here, or rather here. Like they see the blue component in this, even though for me, this looks much more like a red than a blue. And they see the yellow component here, even though for me, this looks mostly like a green. And again, protonormally is the same. And now the people that don't see blue, for them, this actually looks just like a regular red-green contrast because they don't perceive the blue component on either end of this gradient. Okay, so colorblind friendly scales are no magic bullet. So one thing that you might think is, well, okay, I don't really understand color blindness. I don't understand anything about colors. But if I use a certified colorblind friendly scale, I should be good. And the answer is no, you won't. And the reason is that color perception is actually strongly linked to the size of the area that we color. So these are 4 colors from the Okabe-Ito scale. And this is, I write original because I'll again do the simulation of color blindness here. But so I pick the 4 colors and I show them in large swatches, and then I have thick lines, but lines by their nature are thin, right? But thick lines, thin lines, and then dots of various sizes. And what you may notice if you look at this is it's much easier to distinguish these colors here than say these colors over here. In fact, over here, like on my 4K super like high, it's the LG Superfine monitor from Apple. It has the best color resolution I've ever seen on any monitor. And these 2 colors here, where's my mouse pointer? These 2 colors I can barely distinguish. Over here, sorry, the blue and the green, it's night and day. But these 2 here barely distinguish. On my laptop screen over here, I cannot distinguish them at all. And even these 2 here, I can hardly distinguish. Actually, these lines here, I also can barely distinguish. I see that the top 2 are different from the bottom 2. But if I didn't know which is the blue and which is the green, I might not get it right. So that's because the smaller the surface area, the more difficult it gets to see colors, even if we have good color vision. So now you throw color vision deficiency on top of that. So color vision deficiency means it's even harder to see colors even if they're in large areas. So then what happens is it gets even more difficult to distinguish, right? But actually these 4 colors, like so these simulations are always difficult. So I assume in the simulation, like if you have color vision deficiency, you probably already know what I'm saying, which is you can distinguish colors when they're in large areas, but you can't distinguish little dots or thin lines or so. But if you don't have color vision deficiency, then this slide is meant to give you a sense of what happens, right? So these are 4 colors that most people with color vision deficiency can distinguish. And these 4 colors look clearly distinct. These look clearly distinct. These look clearly distinct. But these 2 colors, they look very similar. These 2 colors, they look very similar. These, they look very similar, right? Also, these look very similar. If you already have some deficiency in seeing colors, and then you have to distinguish colors with very, very thin lines or small dots, it gets really difficult. So what that means is, if for you as a visualization designer, you cannot just slap on a colorblind friendly scale and assume all is good. You essentially still have to do these simulations and make sure that they look fine. Or you design your figure in such a way that even if color information was completely removed, the figure would still be okay. By say that obviously, well, actually, it can work in all cases. If you distinguish categories you can maybe label the categories in addition to using color. Or if you have a numerical value, you can have a color scale that goes from a dark color to a light color. So even in grayscale, it looks fine, right? But if you want to be really certain, you should run these simulations and see what happens. And or even better, if you have a friend who has difficulty seeing colors, show them the figure and ask them how the figure looks to them. Okay, and so there is an R package that is maintained by Achim Zeilheis, and he has done a lot of work recently on that. I've made some minor contributions where there's a lot of tools. If I assume most of the audiences are, everything I've said so far is completely agnostic to the software that you're using. But so now we're getting into the R specific part. This package does a lot of things with colors. I could not have written my book without that package. And for one, it actually has a large number of different color scales that you can use. This is just a small subset of the color scales that are provided. So you can like try them out and see how you like them. So it also has a lot of possibilities to make your own color scale. So this, for example, I'll actually, if there's still time, get into that in a little bit. But so this is a circle in the HCl color space, and that makes you something like this color scale is something like this one here, or maybe this one here. So that's how these color scales are made. That's actually how the ggplot hue scale is made. It's a circle in HCl color space. And then it also has an app that I wrote that allows you to choose colors. And again, if we have time, I'm going to demonstrate that. I wrote that app because I just couldn't find what I needed anywhere else. And it also has an app that allows you to simulate different color visualization deficiencies. So you give it an original image, and then it gives you the desaturated image and various different color vision deficiency simulations. There's this app, which is part of the color space package, which works great, but it requires a bitmap image. And then there's a different app that I wrote together with a graduate student here at UT, Claire McWhite, which just takes something like a ggplot object and works on that directly. There's pros and cons. That package we've never put on CRAN, and there's some technical reasons why I cannot guarantee that it will always work on every plot, and for that reason, I don't want to put it on CRAN, but it works well, and I like it, and I'll also be happy to demonstrate that. And with that, let me go to my acknowledgements, which this is really the acknowledgements for the book that I wrote and the R packages that I've used to write the book. And so then at the bottom, the funding is mostly for the biology, which I didn't talk about. And the book was mostly my own project, but there were a lot of people that created the environment in which I could write that book, do all this work, and or get feedback from them. And so those are all people that in one way or another have influenced me doing the writing and the book before and after. Okay, so that is my prepared presentation.
So Klaus, I think now would be a good time just to take a couple of questions.
Okay.
I think we have time for you to show us one of the demos of the Shiny app that you envisioned. But I'll ask a question that sort of was came up in the comments, a bit of a discussion in the comments while you were going through some of your examples, to try to like summarize it. And while I'm going through this, anyone else that has questions, go ahead and ask them in the comments now. So when you talked about your 4 different types of uses of color, one that could be added or maybe folded into your examples is the use of color that then maps to something in real life, right? And you talked about the red-green color scale problems and quintessential heat maps and so on. But when you showed your example of the median salary across the different counties in Texas. One question that came to my mind is, would you ever consider using green, the darkest green, let's say, as the richest, and either a lighter green or a color away from that, thereby mapping the color that we associate with money, at least in this country, with the visualization tool? And that then is reflected in a conversation that was happening in the comments about maybe mapping color to values, let's say on a map, where a high color at a high altitude is white because of snow, and a low altitude is going to be green because of not snow, and basically mapping color to physical attributes in real life. How do you think about that? And would you define this as its own category, or would you define this as a subcategory of one of the four that you talked about?
I honestly think it's a subcategory of the four, because all examples that I can think of will in the end be one of those four. So your example with money, so you'd essentially have to have a sequential scale that just is very green on one end and very non-green on the other end. And the green is a design choice, but the color scale, if it's meant to represent values of money, should still be reasonably sequentially, perceptually uniform, right? So you need a proper color scale that goes to green. And then the other situation where I could envision it, so actually a scenario where I think this happens all the time is in a political context. Let's say in countries that have more than two prominent parties, you may want to color some visualization. Let's say they are like number of seats in parliament or something like that, by the colors that represent the parties, right?
Yes.
And so it's really a categorical color scale at that point. And you're running into the issue that depending on the colors that the parties have chosen, it may be a poor categorical color scale, right? Because a categorical color scale has categorical color scales are the most difficult to design, in my opinion, because you don't want one category to be highlighted among any others. You don't want there to be any sort of perceived order. You don't want two categories to be closer to each other than the other categories, right? If you have three blues and one red, well, you again have a problem. It's not really a categorical color scale anymore, where the four categories are all clearly distinct. So it gets really difficult. And this is actually sort of one of my pet peeves. When people design color scales by taking colors from movies, like Wes Anderson scales, the colors are great. I love the colors in his movies, but you end up with things like you have a 5-color scale and there's 3 blues and a yellow and a green or so, or red, and you actually have created a highlight scale rather than a categorical scale. So you have to be really careful with that. And I think wanting to use colors from that have some sort of natural interpretation from the object that you're representing in the visualization, it's a trap that you could fall into.
Okay. Well, then related, a great follow-up then is, can you recommend other color packages like Viridis, Psycho, or PALS?
So Viridis and Psycho, they're actually 3 very different things, if I remember PALS correctly. So Viridis and Psycho, they both have, the intent is to have carefully designed color scale. Sorry, I need to be correct in my wording. Perceptually uniform color scales that are useful in specific purposes, in specific circumstances. I think PALS is just everything. Or maybe I'm confusing this. There's the Palettier package, which is just any color scale that anybody has ever developed. And there's nothing wrong with that. It's actually a sort of a problem that we have all these different color scale packages, and it's more confusing than helpful. But there are color scales out there that do not serve a good data visualization purpose. Also, if you look at, like, if you just go to a random website about picking colors, like Google material design or whatever, those are typically, they're designed with a different purpose in mind, right? These are color scales to color your app or to design a user interface. It's not necessarily the same as making a data visualization. So that's just something to keep in mind.
Okay, so at this point, for those of you who would like to stick around, I'd say Claus will take maybe another 10 minutes or so. You can go ahead and switch over to the Shiny app that you were talking about. And this is going to be a deeper dive into some technical considerations.
So I'll actually start elsewhere. I'll
Okay.
start with an illustration program. Actually,
Okay,
it
perfect.
doesn't matter. Because, so now we really have to talk about color spaces, right? If we just use color palettes that somebody else has designed, then we don't have to think particularly about color. We can just pick a, like, let's say the color space package is probably the package with the largest number of different colors that are grouped into categorical, qualitative, diverging, and so on. You can just pick any of those color scales and they will serve the purpose that they're annotated with, and then it's just, you pick what you like, and that's totally fine. If you want to make your own color scale, then you need to start to pick colors, and that means you need to know something about colors. And so where do you start? Well, most people are familiar with, sorry, I've lost my mouse pointer again. Where is it? Somewhere stuck. Ah, there it is. Okay. Most people are familiar with color picker dialogues in illustration software. So this here is Affinity Designer. I don't have Illustrator, so I can't speak to Illustrator. I went through 4 or 5 different paint or drawing programs that I have and looked at the color dialogues. This is actually the best one that I found, and it still has various shortcomings. So if I pick here on fill color, so this should pull up the dialogue. Okay, so this is probably a standard color dialog that you have seen. So this is RGB hex sliders here, red, green, and blue, right? This is how computer monitors create colors. They make a mix of red, green, and blue, and then you end up with this hex code. Here's F71800. That means there's no blue, there's a little bit of green, and there's a lot of red. So now if I start mixing green into the red, then I create a color that is yellow, right? Like if I turn on red and green full blown and blue full off, then I have full on yellow here, FFFF00. And if I maybe want to have a yellow that is just a very light yellow, then I can mix in some blue also. And so now I'm getting a yellow here. And you see the sliders actually here, they show what the color will be as you slide. Right, so green is full on now. If I start removing green, then I'm going towards purple, right? Because purple is red and blue and little green, right? So now I'm in purple, and I can play around. I can make a very strong purple, or if I want to have a lighter purple, I can mix some green back in. There's a couple of things that you may notice. One is this is ridiculously small, right? You can barely see it. I can barely see it on my large 4K screen, and I actually scaled up I picked the largest font I could pick in this app. I scaled down the screen, and still I can barely see it. That's a problem. We can't really, we just talked about how difficult it is to see colors when it's small areas. So this is a problem. Now it has swatches where I never used the software, so I don't know how it works. And gradients are a bit larger, but normally I would want to use sliders to pick colors. Now, if you have ever picked colors with RGB sliders, you may have experienced that you don't really understand them. Now, I'm making assumptions, so I'll speak for myself. I don't understand them. if you tell me, make me a color that looks like this or that, like make me a red that has a little bit of a purple tone to it, but I want it to be really more of a gray red, not a strong red, I really don't know how to make that color with RGB. I could probably by now, I know enough about colors that I probably could do it, maybe. What did I say? I want a purplish red that, however, is more grayish than, like, not that strong. So, okay, it's getting dark here, but let's say I don't want it dark. I want it light but grayish. Then I need to throw green back in. But then I also need more blue and more red, but it's still like sort of, it doesn't have any gray at all yet, right? So it's really difficult. I would say it's so difficult to pick colors with RGB sliders that honestly, you should just never do it. Don't pick colors in RGB space. You will not succeed, and your colors will look bad. So this comes to the point of, you may have heard color spaces. Like everybody talks about color space, and actually when I click on this here, I have RGB hex, that's both the same thing. And then it is HSL and CMYK and lab. And what are those things, right? So what they are is there's different ways that we can organize colors. So the colors are always the same, in particular on a monitor. Like each monitor has a set number of colors that I can display. And so usually we're using 3 8-bit integers, right? So here in hex, I have a 2-digit hex number and another 2-digit hex number and another 2-digit hex number. So that is, a 2-digit hex number has 255 values, 8-bit. If I have 3 of those for red, green, and blue, I have 24-bit colors. And so that is the total set of colors that a modern monitor screen can show. Any color that can be represented with the 24-bit integer numbers. And that's how sometimes you hear numbers like 16 million colors or so. I think that's the number. I don't quite remember. But so this is the set of colors that exist on your screen, right? And now the question is, how do you organize these colors so you can find your way around them? So you may have heard of CMYK. That's a color space that actually is for printing. And so we, in practice, unless we design like booklets or things like that, we don't ever interact with the CMYK color space. So even though I remember like when in 2000 or so, the GNU image manipulation program, GIMP, came out first, and people were having discussions over whether it's professional or not because it didn't have the CMYK color space. You really need it for print design, and you don't ever need it for anything else. So there's other color spaces that are much more important, and the most important one is missing here, actually. But before we go there, we have HSL, and there's HSL 2 different ways that it's presented, as sliders and as wheel. I like the wheel a bit more because it's actually a little more useful. So HSL, hue, saturation, and lightness. So you always need 3 numbers to specify a color, except CMYK, which needs 4. I'm not going to get into that now. But so it's essentially of red, green, and blue, but you do a coordinate transformation and you pick different coordinates. So HSL, hue, saturation, lightness. So the hue is just which color it is. So the hue is the circle around here. So you see when I circle around, the hue changes, but the saturation and the lightness stay the same, right? And so like with my challenge earlier, pick a red that is a bit of a bluish component to it. So I could pick maybe this over here. And now saturation and lightness pick how colorful the color is. So this is a very colorful color, and this is a very drab color. So if I go along this dimension, you see the lightness stays at about 50, right? So that's exactly 0 lightness sorry, 0 lightness is black, 100% lightness is white. So 50, this is a 50% gray if I have no saturation. And then if I increase the saturation, then I have this the most colorful color, and this is the most grayish color, and I can go in between. And so now I have a color that is sort of grayish but has this hue that I wanted. And now if it's too dark for me, I can go further here. I can make it lighter or I can make it darker, right? So this is actually a reasonably good way to pick colors, but it still has some issues. And so this is the HSL color space. You may also sometimes see HSV or HSV, which is closely related but not the same. HSL is better than HSV in practice. So the difference between different color spaces is really they organize how we in our mind think about colors. And so if you think in HSL, then HSL is the right space for you to choose. If you think in RGB, then RGB is the right space for you to choose. I would just say in practice, you think in neither, and that's why neither of those color spaces is appropriate. Now, there's another one, which is LAB, L-A-B, which is actually the right space to use, except it's still the wrong coordinates. Like LAB has here lightness, which goes from extremely light to extremely dark. And then it has A and B are two arbitrary coordinates. And I would argue that you will not be able to pick in the lab space the color that you want. But there's a closely related color space, which is the HCL color space. Hue, chroma, lightness. Very similar to HSL. HSL, hue, saturation, lightness. HCL, hue, chroma, lightness. And that's the space that I typically use. And so that is this app that comes with the color space package, which allows you to pick colors in the HCL color space. And the first thing you may notice is it's much bigger, so you actually see colors quite clearly. Let me go to the hue chroma space. So you may remember when I just showed you the HSL, we had the outer ring, and then we had the triangle in the middle. And so here the ring is this. So the hue is essentially the same as before, right? Let me just make it a little more chromatic. So there's one thing that you may notice right away without me even explaining what's going on. So I have to reduce chroma. There's these weird patches that are missing, right? Okay, so let's stick with this. So I have here this circle. So this is the hue chroma plane. I'm showing you the hue, which is what color it is, blue, red, green. And I'm showing you chroma, which is how colorful is the color. And then I'm not showing you the lightness because the light or luminance, the luminance is in the luminance chroma plane. So I can move around this circle here, and it's written in shiny, and it's not quite as fast as you might want it to be, but it's fast enough. It works, right? So here I'm picking different colors along the circle while holding the chroma and the luminance the same. And so this is, for example, how you make a ggplot color scale. You just, like ggplot hue scale, you just start here, you pick that color, then you move along a little bit, you pick that color, you move along a little bit. I actually think ggplot comes from the other side. I apologize about that. So it'll take me a little bit to get the whole thing. Sorry, I'm getting impatient and taking larger steps, but you may see, you may recognize this has very much a ggplot feel to it, right? That is how the ggplot hue scale is generated. And because you're keeping the luminance and the chroma fixed, you're guaranteed that none of these colors stand out. They truly differ only in the hue. And if you go in even steps, you know that they're all sort of nicely spaced out. And you can take as many steps as you want. And so this is why this is the default scale for categories, because if somebody asks ggplot to distinguish 100 categories, ggplot will do it. And no judgment on the part of ggplot. There may be judgment on the part of the people that implemented the code, but ggplot will do it, right? It will generate 100 values categorical scale by just taking really tiny steps around this circle. Okay, so now what's the difference between this color scale, this color space, the HCL space, and the HSL space? It's actually very subtle, but it's very important. So here I have the chroma, and actually let me go to the luminance chroma plane, because that is sort of similar to, let me go back here to the color wheel. So this triangle here, it's very similar to this thing here, right? So I'm holding the hue fixed. The same. Why does this? Sorry, this always pops. This disappears when I change my screen. But so I'm holding the hue fixed, which here is this purple, and then I go with that hue from very colorful to very gray and very dark to very light, right? And I'm doing the same here. I'm holding the hue fixed and I'm going from very light to very dark and very gray to very purple. But the difference is this triangle always has the same shape, right? I can go over here, I can go over here, I always have a nice triangle, which makes the programmer happy. It seems to be logical. Versus here, if I change my hue, the triangle changes shape. And that's sort of weird, right? And that's scary. And that's why we don't intuitively like the HCL color space and why most people don't implement it. But where does this come from? So where this comes from is the following. So let me pick this blue over here, right? It's a very strong blue, right? It's a color that is not particularly light. So the luminance is 38. Remember, 50 is sort of the midpoint between light and dark. So it's on the darker side. It has a very high chroma here on the chroma on the range from very gray to very colorful. It's very high. Now let's say I want a yellow that is the same darkness and the same strength of color. It's yellow, it's not blue. And what happens is that color does not exist. So I'm over here. I switch to the hue chroma plane. So remember, chroma in the middle, zero chroma means it's gray, and here it means very colorful. And then the circle is the different colors. And so if I go along the circle over here, this would be a yellow, or maybe over here. This would be a yellow that is as intense yellow as the blue is blue, but it's as dark as that blue. And the fact is, this color is impossible. It does not exist. If I want a yellow, I have to accept that the yellow is going to be much lighter than the blue. So I need to increase my luminance. Now that I cannot make a blue that is as intense but light. But now we're getting to the point where I can possibly choose the yellow, right? So now I have a very strong yellow, right? Very intense yellow. What you see is every time you get into the extremes, right, a very intense yellow, you're sort of at the boundary of the HCL color space. Now again, I cannot pick a blue that is as light as this yellow, but intensely blue, right? It's physically impossible. And the HSL color space, it sort of glosses over that fact, right? I can pick a very intense yellow, and now I can keep the saturation the same and the lightness the same. Sorry. Keep the saturation the same and the lightness the same, and swap over here, and there we go. I have a blue with the same S and L values. So the reason that that works in SSL and not HCL is that in HSL but not HCL is HSL is a relative measure. So the saturation, importantly, is sort of the maximum blue for the blue, or the maximum yellow given that you're yellow. So you're really representing relative colors. And that's fine with, like, if I have decided on this hue, this triangle is perfectly useful and reasonable, but I cannot compare between colors. But the moment we want to choose a color scale, and in particular categorical colors, we really want to compare between colors, right? So let me get out of here into a space where I can operate a little better. So let's say, for example, here, actually, sorry, I'll just quickly, oh, clear. There we go. No color palette. So in particular, what you usually find is that at the extremes of chroma, if you go to very colorful colors, then the color space starts to get smaller, right? So for example, now you may start to understand why there are these interruptions. So I can, like, along the hue, I can pick a pinkish color. Pink would be over here. With this chroma and luminance, I can go to the blue. But now here, these colors don't exist, right? And that's where this gap, and then so that gap corresponds to this region. And now I go again into the colors that exist over here. And then again, there's a gap. And then again, I have colors that exist.
All right, Claus. So let me try to summarize some of the things that you're saying.
Yeah.
If I can. So
sure.
So there's a couple of things that are really clear. So the first thing is you've thought deeply about color. The second thing is I no longer feel qualified to say anything about color, let alone choose any colors. One of the first
That's
things
because I need 3 more minutes, because now we'll come to the take-home messages of what you do with the app. But anyway, summarize first.
Okay, so actually that's what I was trying to get to, is like some of these take homes, because in the very first part of the presentation, you said for unless you have a very specific reason or very specific purpose, you should probably stick with defined color scales, right? And you laid out some of the different color scales. So I was going to ask, so we'll go back and switch back to your presentation, but I was going to try to then summarize, but I'll let you do it. The very concrete sort of recommendations for people should they want to begin to explore some of their own color scales.
So I think the first recommendation would be go with existing color scales, right? There's a lot of them. Just try them out. And then if you feel too limited in that, then start thinking about the HCL color space. And so I think the reason, if I can, I know we are already half an hour over, but if I can have 2 more minutes explaining why it matters. So you can pick a hue, and then in this triangle, basically just create a path and create a reasonable color scale by just going from a dark to a light color. And it doesn't have to be perfectly linear. It's fine to like go around. So there you go. Just picked with basically no thought at all, a reasonable color scale that starts, and you might have like some starting color from somewhere, We talked about the green, right? You may want to make a green color scale. I'll not do it now, but that's one way to do it. So that's how you can create color scales that you like. This would be a sequential color scale, and for a categorical color scale, you generally want to move around in a circle. So for example, you could pick clear, I pick a color here, and then I pick a color here, and I pick a color here, and I pick a color here. Now, the one other thing is, most people, when they pick colors, and in particular, RGB color space almost for sure, but HSL color space also, pick colors that have too much chroma. So you may notice these colors that I picked here, which I would say look reasonably pleasant and elegant, they have really low chroma, right? So this color here, it has 35 out of a maximum of, I guess it's 180. Let me just pull this slider all the way to the right. So that was a bit too far. Still too far. Sorry, I was overly ambitious. It really is about here. Still not there, sorry. Okay, this is good enough. So versus this color here, right? If we compare these two colors, they have the exact same hue. They have the exact same lightness or darkness, or actually luminance is the technical term in the HCl color space. But this one has much more colorfulness than this one. And colorful colors are associated with children's toys. If you think about what do toys look like, they have high chroma. They're on the high C spectrum. The Google colors, high chroma. If you think about elegant colors, if you look like in my background, there's nothing in this room. I'm not saying it's a particularly elegant design, but there's nothing in this room that is a high chroma color. Everything is very low chroma. If you want to design color scales that look more elegant, you will generally want to lean towards lower chroma. That's probably like, if there's like a single take-home message that I have, that I repeat over and over when it comes to color, is reduce the chroma. And actually my criticism of the Verde scale is too much chroma. It's too colorful.
So then to fix that, perhaps you would then maybe, as you did with some of these other subdued hues that you made of the your own color palettes, you could do the same thing perhaps with Viridis. You wouldn't call it Viridis Light, that's already taken, but something similar to tone it down. So we are a little bit over. That's okay. We've got still a handful of people that are sort of have high endurance and are with us all the way to the end. We will just, if there are any burning questions, there's one, actually two questions that came up. I might as well take just a moment to ask. And so one, I'm just trying to scroll through it here. One was, what's your opinion about binned scales that are based on summary stats, quantiles, for example?
So there's two questions in one, and I'm not entirely sure about the second part. So let's talk about bin scales. Bin scales are actually preferable to continuous scales. And my book uses too few bin scales and too many continuous scales, and that's because bin scales weren't really available yet in ggplot. Really bad reason. And the maybe slightly better reason, I didn't quite understand the importance of binning at that time. So if, let's say you have like median income, right? If I bin it into 5 categories, I end up with 5 colors that should be sequential, right? It should be a sequential scale. But if I have 5 distinct colors, I can actually tell exactly into which bin each individual color falls. Versus if it's this continuum, we can't actually perceive the continuum very well. And so it gets very difficult. Like, it looks better to have a continuous scale, but it's harder to read and harder to interpret. And so actually binning is a good idea. as long as you bin uniformly. And so I guess I don't know that I would bin by quantiles. I think I would bin by uniform bins in the data space. Like medium income, okay, 0 to 100, 100 to 200, 200 to 300, 300 to 400, or something like that.
Okay. One other question here, and then perhaps we'll wrap it up unless anyone else chimes in. So one is, one of the attendees said, I would argue if you found a good color scale from some of the packages to be weak or not sufficient enough for your data analysis, that you should think about other encoding of data not to create a better a palette. So this gets back to a data visualization, I think, question, and about a little bit like your Delta and American versus all of the other airlines. Instead of coming up with, colors for all of the airlines or trying to come up with some other strategy, you should then say, well, what's the main message that I'm trying to portray with this data visualization element, rather than thinking about rearranging a color palette. So do you have thoughts on that?
Yeah, I'm not entirely sure I agree. So first of all, sure, you should always experiment and see if there's a different way of showing the same data. And certainly as I was writing the book, I ran into this a lot where like I would look at the data set in one way and I would see a pattern and I was like, oh, now let me show this in color. And then the colors wouldn't really show the same thing. And colors in particular, like we go back to the medium income, whether you have like a continuous gradient where like the median income slowly rises to a certain point, or maybe like everybody has low income and then in a few places you have very high income, so you have sudden jumps. Those two different scenarios can look very different in different color scales. And so I certainly, like I saw cases where I felt like there was a pattern in the data that I knew was there because I had looked at the data long enough, and some color scale would just not show it, versus a different color scale that was just as valid would show it. And I don't think at that point we're manipulating, or maybe manipulating our perception. I mean, color perception is not that great, and like sometimes we see the wrong thing if we use some weird color scale.
Okay, well, I think that's a fantastic point to end on. So you got a lot of love in the comments for your book, for the continual package development that are helping the average data visualization enthusiast make better visuals. So I will also extend my thanks for your packages, which I use extensively. So thank you for your time, and this has been a really fun session.
Yeah, it was fun for me also, and thanks for everybody who tuned in.